Next is a problem that suppose we have a satellite of mass m which orbits our Earth in a circular orbit of radius r0. Okay, and suppose one of its engine is fired briefly toward the center of Earth by changing its orbit, by changing its energy and not changing its angular momentum. Okay, the problem is our satellite is fired by one of its engine to change its orbit towards the center of Earth without changing angular momentum. The question is, what will be the new orbit? Okay, so initially it was circular orbit. What happened after firing the satellite by changing its energy? Remember, not changing its angular momentum. Okay, let us understand this problem. For that I am first I am drawing the energy diagram. So energy diagram is this one. See, in this problem, this the R is this the energy and use effective energy as a gravitational potential plus L square by 2 mu r square, that is U effective. This one, this is the shape, and since it is circular orbit, you know this E is equal minimum case, this is R0. So R0 is the radius of the orbit of the satellite. Okay, the initially it have energy EI. Okay, and what about its center of mass? So center of mass is one is Earth and one is satellite. ME is the mass of Earth and M is the mass of satellite. So its reduced mass is MEM by ME plus M. Since mass of Earth is very much bigger than mass of satellite, M is plus M is approximately equal to ME. Therefore ME and ME cancel. So reduced mass is approximately equal to the mass of satellite. Okay, and I am assuming the orbit is not so much varied. Okay, so that the change in energy is very small. That means EF is the final energy, and EF is not much greater than EI. And the new radius, this one, okay, that is a bound system now, you know, so there will be oscillation. In a bound system there will be oscillation, and it will possess a simple harmonic motion with some frequency. Okay, this you have learned in last semester also. It is better to refer those points once more, where we have learned about the potential and all. Okay, it is given in the book itself. Okay, and you know R and R0, R is the new radius of the orbit, and I think R and R is not much differ from R0. Okay, it is not so much differed from R0, almost close to R. All right, so thus what I am doing is U effective in R for the new orbit. I am calculating U effective in the neighborhood of R0. That means in the neighborhood of R0 means R and R0 is almost close each other. Therefore U effective R is equal to minus GMEM by R plus L square by 2 mu R square. Here remember L is not changed, so it is minus C by R, because GMEM is a constant. I have taken it as C, minus C by R L square by 2 mu R square, that is the effective potential. Okay, now so what will the minimum is happen at R is equal to R0. At minimum the slope is also 0. That means du by dr at r is equal to r0 is 0. So I am differentiating u effective, that is c by r square minus L square by mr square at r is equal to r0 is equal to 0. That implies c by r0 square minus L square by mr0 cube equal to 0. From that L is equal to square root of mc r0. Okay, m is the mass of satellite. So earlier we have learned u of r is equal to, in the last semester we have learned u of r is equal to constant plus half k r square, where k is d square u by dr square at r is equal to r0. Okay, so using that idea, k is equal to d square u by dr square at r0. I have first differential c by r square minus L square by mr cube. Differentiating once more, I will get minus 2c by r0 cube plus ml square by mr0 raised to 4. Okay, but L is square root of mc r0. Substituting value of L, what I am getting, k is equal to c by r0 cube. Okay, you do this calculation. So therefore k is equal to c by r0 cube. While knowing k, we can calculate the frequency of the oscillation. Why the frequency? Since it is a bounded one, there will be oscillation, and the frequency of oscillation, is root k by m. I denote it by beta. So therefore beta is equal to root k by m, and this is equal to k is c by r0 cube, that is root c by mr0 cube, that is equal to L by mr0 square, so knowing the value of L. Okay, that is beta is equal to L by mr0 square. Okay, that is the oscillation frequency. Now let us calculate the radial position. So what should be the radial position? Radial position means the new orbit. Okay, so since it is a harmonic motion, we can say r is equal to r0 plus a sin beta t. Okay, r is equal to r0 is the initial radius plus a into sin beta t. Why we are using the oscillating term? Because it is a bounded system. In the bounded system, it will constitute a simple harmonic motion. But you can ask me one question, that why you cannot use the cos beta t? So I can use cos beta t, but I cannot keep that by using cos beta t at initial time t is equal to 0. Cos 0 is 1, therefore r will not be equal to r0. Okay, so that will be r is equal to r0 plus some constant. In order to avoid that complexity, I choose a sin beta t. At t is equal to 0, sin 0 is 0, therefore initial value of r is r0 itself. Okay, but as we know, beta t is theta. Okay, sin theta, that is theta is equal to beta t or L by mr0 square into t, or r is equal to r0 a sin theta. So if you can see this one, the red one is the black one is the first orbit r0 radius, and the red one is, see this, so the red one is the new orbit, but you can see that both have almost circular in shape. Okay, and r is the radius. But one thing you have to remember is both have same circular shape, but the center is differed. The center of the first one is the center of earth, but for the second one was not at the center of earth, it is changed. Okay, from this r, this is a is the amplitude, this distance, the difference between amplitude A. And one thing you have to remember is what we get is beta is L by mr0 square for the oscillation, and also for radial motion it have the same frequency. That means the frequency of rotation is identical to the frequency of radial oscillation. Okay, so both have identical oscillation frequency, that the rotation and oscillation have the same frequency. That's very important.